And let's continue watching this guy. Okay, is it interesting to you? Or shall we switch to anything else?
It's okay.
Good.
Now, if you followed the news at the time, you'll have seen a physicist getting very excited indeed, and you'd be forgiven for thinking we get away every time we discover a new particle. Well, that is kind of true, but the Higgs boson is particularly special. We all got so excited because finding the Higgs proves the existence of a cosmic energy field. Now, you may have trouble imagining an energy field, but we've all experienced one. If you've ever held a magnet close to a piece of metal and felt a force pulling a gap, then you felt the effect of a field. And the Higgs field is a little bit like a magnetic field, except it has a constant value everywhere.
Georgie, so Higgs boson, it has a field, right?
Well, at least it proves the existence of the field, so probably yes.
Oh, yes. What is a field? He tried to explain it very primitively. He told about a piece of metal and a magnet. How can you explain primitively what does field mean?
Well, the process of bodies pushing each other towards or backwards.
Yes, wonderful explanation. So there's nothing between these two pieces, but somehow they react, right?
Yes.
I mean, there's nothing between a piece of metal and a magnet, but somehow it is metal feels the magnet and the magnet feels the metal, right?
Right.
And he says that Higgs boson has a field, and this kind of field is everywhere. So in your room, in my room, in his place.
It's all around us right now. We can't see it or touch it, but if it wasn't there, we would not exist.
What is his conclusion, Georgie?
That without the field we wouldn't be?
Thank you very much. Without a field of this tiny particle, we wouldn't exist.
The Higgs field gives mass to the fundamental particles that we're made from. It wasn't there, those particles would have no mass and no atoms could form, and there would be no us. But there is something deeply mysterious about the Higgs field. Relativity in quantum mechanics tells us that it has two natural settings, a bit like a light switch. It should either be off, so that it has a zero value everywhere in space, or it should be on, so that it has an absolutely enormous value.
What is crazy about this Higgs boson?
Well, that its value is quite extreme all the time. It is either very small or very big.
Wonderful. And he gave an analogy with a light switch. What kind of analogy?
That it is either on or off.
Wonderful. If the light switch is on, everywhere in the room, what?
It will be darkness.
Okay. If it is on, it will be everywhere light, right?
Right.
It is if the switch is off, everywhere it is darkness. Okay.
Yes.
In both of these scenarios, atoms could not exist, and therefore
But what is interesting, in both of these scenarios, he said, atoms would not exist. And listen.
all the other interesting stuff that we see around us in the universe would not exist. In reality, the Higgs field is just slightly, not zero, but 10,000 trillion times weaker than its fully on value, a bit like a light switch that's got stuck just before the off position.
Okay, Georgie, it's a crazy explanation. How do you understand? Where is the switch? He gave us another analogy.
I'm afraid I couldn't hear some of it.
Okay, he said that this Higgs boson, this particle, is neither in on position nor in off position, in somewhere near the off position. He says, let's imagine that the switch is stuck.
Oh, I see. It is like in the middle.
He said it is stuck near the off position, not in the middle. Okay.
Yeah.
Okay.
And this is crucial. If it were a tiny bit different, then there would be no physical structure in the universe. So this is the first of our dangerous numbers, the strength of the Higgs field.
Okay, so the first, a very strange and very dangerous number, which one? That this switch, this Higgs boson, not in on position, not in off position, it is somewhere near the off position. But he said, Georgie, if the switch, the field of Higgs boson were in any other position, what would be with the world?
Well, it wouldn't be any same.
Thank you, around us. No Georgie, no me, no this guy, no one, no universe.
Well, probably there would be something else. Perhaps.
Don't know. Maybe you're right.
Theorists have spent decades trying to understand why it has this very peculiarly fine-tuned number, and they've come with a novel explanation. Have sexy sounding names like supersymmetry or large extra-dimensional. Into the details of these ideas right now. But the key point is this. If any of them explain this weirdly fine-tuned value of Higgs field, then we should see new particles be at the LC along the Higgs boson. So far, though, we've not seen any sign of them. But there's actually an even worse example of this kind of fine-tuning of a dangerous number, and this time it comes from the other end of the scale, from studying the universe at vast distances. One of the most important consequences of Einstein's general theory of relativity was the discovery that the universe began as a rapid expansion of space and time 13.8 billion years ago, the Big Bang. Now, according to early versions of the Big Bang theory, the universe expanding ever since, with gravity gradually putting brakes on that expansion. But in 1998, astronomers made the stunning discovery that the expansion of the universe is actually speeding up. The universe is getting bigger and bigger, faster and faster.
Okay, tell me, Georgie, we talked about what happens to universe.
Well, that it is expanding ever faster and faster, and this was the most important discovery of the recent time.
Driven by a mysterious repulsive force called dark energy. Now, whenever you hear the word dark in physics, you should get very suspicious, because it probably means we don't know what we're talking about.
Georgie, he said, when you hear the word dark in physics, be very careful, and please read.
Because it probably means we don't know what we're talking about.
Yes. Physicist, he says, physicists don't know what we are talking about. Translate, please.
Физики не знают, о чем идет речь.
Oh, yes. Thank you. But we have black holes, we have dark numbers.
We don't know what dark energy is, but the best idea is the energy of empty space itself, the energy of the vacuum.
Georgie, please read the caption.
The energy of the vacuum.
Good.
Энергия вакуума.
Oh, wonderful, Georgie.
Huh.
Wonderful. Dark energy. It's a crazy force. It's an energy of the vacuum. How can you explain? How could it be? What is vacuum, Georgie?
Well, vacuum is absence of space inside inside a container.
Great. If there's nothing inside a container, how can it be a lot of energy inside a container?
Well, probably none.
But it's not so. It is not true.
Yeah, well, that's the point.
That's the point. That's the point. That dark energy, which we cannot understand what it is, but in a vacuum there is dark energy and there is crazy number of energy. There is crazy number of energy in a vacuum. Okay, wonderful.
Now, use good old quantum mechanics to work out how strong dark energy should be. You get an absolutely astonishing result. You find that dark energy should be 10 to the power of 120 times stronger.
Please read. How much is dark energy? It should be
10 to the power of 120 times stronger
than the observed.
Than the value we observe from astronomy.
From astronomy. That's 1 with 120 zeros after it.
Yeah, it's a big number.
Please read what kind of number it is.
It has 120 zeros after it.
This is a number so mind-bogglingly huge.
Please read.
This is a number so mind-bogglingly huge
that it's impossible to get your head around. We often use the word astronomical when we're talking about big numbers. Well, even that won't do here. This number is bigger than any number in astronomy. It's 1,000 trillion times bigger than the number of atoms in the entire universe.
The number is much bigger than the entire...
The number of atoms in the universe.
Oh yes, that's the crazy stuff. How much the energy is in dark matter, is in dark energy. How much energy is in vacuum. How much energy is absolutely empty space.
Well, it appears that a lot.
Appears that a lot. Georgie, I would like to listen to your teacher of physics. I'm not a teacher of physics. I don't understand it at all. I don't understand it at all. And this guy, he's clever, of course, but I don't believe him. What about you?
Well, he's talking about fascinating stuff, and I want to believe. The only thing is that he doesn't really give sources where he gets that information.
Oh yes, but no, probably I wouldn't listen to him at all if he wasn't one of the scientists who works in Switzerland at this huge collider. He works there, and of course you know that it's a multinational thing, that collider, and scientists from all over the world are working there, from Russia, from France, from America, from Japan, from all over the world. Of course, it's a big competition to choose somebody who will be sent to work there. Why? For example, we would like to send somebody from Russia to work there. Why it would be a very big...
Because it is prestige for the country.
Good idea. It's good idea. In this case, somehow I have to believe him, but on the other hand, I don't understand what he's talking about.
So that's a pretty bad prediction. In fact, it's been called the worst prediction in physics. And this is more than just a theoretical curiosity. If dark energy were anywhere near this strong, then the universe torn apart, stars and galaxies could not form, and we would not be here. So this is the second of those, the strength of dark energy. It requires an even more fantastic level of fine-tuning than we saw for the Higgs field.
Okay, so the first dark number, it's the number of X boson. We wouldn't exist if somebody if something will be in other way with X boson. And second crazy number, it's the number about dark energy.
Yes.
Okay.
But unlike the Higgs field, this number has no known explanation. The hope was that a complete combination of Einstein's general theory of relativity, which is the theory of the universe at grand scales, with quantum mechanics,